the entire thing and change a couple of things. So we're not going to play classical, we're going to play quantum. We're not going to keep classical wins, we're going to keep quantum wins. And we're going to use this for our result, like that. And the only thing I need to implement is the play quantum operation, which is of course the hardest part. And now I need to do the exact same thing as I showed you in the slides. So again, it's not very difficult. You first keep a mutable tuple of A and B, which is your output. Let's just set it to false, false for now, and then return that as the result of this function. I also need two qubits, so I'm going to use a qubit for Casper and a qubit for Vlad. And I'm going to use the qubit factory function to create those two qubits. I'm going to put one qubit in superposition and use the CNOT gate to entangle them, and now they're entangled. Then I have those four different scenarios. I have if x equals 1, else if x equals 0, if y equals 1, else if whatever that thing is. All the things inside are basically bullshit. So Copilot knows what I'm trying to do, but he has no idea what I'm actually doing. So X is the left-hand side of the PowerPoint slide, so that is Casper. So set A, so the output for Casper equals. So when X equals 1, we need to measure in the sine basis. So this is M reset. Sine basis is the y-axis. If X equals 0, we need to measure in the computational basis. So set A equals, which is the z-axis. Now for y, we have that minus pi over 8 and positive pi over 8. In Q#, we cannot measure on every basis. We can only measure on the 3 bases, x, y, z. But you can do a rotation. So you can do Rx, which is a rotation around the x-axis for a specific angle, pi over, it's 8, but in Q#, you need to do 4, because the value that you're providing is divided by 2, for some reason. I can show you the documentation, it actually says that in the documentation. So for y equals 0, it's going to be minus pi over 8. For positive, it's going to be, for y equals 1, it's going to be positive pi over. And then you can just measure in the z basis, because now you shift it, you rotate it, so that's going to be the same thing. And if I didn't make any mistakes, and I just run this, how many % chance will we win? 90? Almost. Let's run. Oh, I'm so nervous. Run, goddammit. Where is it?
I think your terminal.
I thought it would open automatically. Terminal. I'm sorry, I know you're hungry.
Either console, probably?
No, it should happen.
Yeah. Maybe you should, output.
Oh.
Yes, there it is. 85.
Oh yeah, 85. Yeah, that's the correct answer. Phew! Now, so this is a very stupid example. It just shows you that in the classical world we have a 75% chance of winning. In the quantum world, when we think outside of the box and do all the weird quantum things, we have an increased chance of winning from 75 to 85, which is not a lot, but it's a cool demo, I hope.